What is the main motivation behind the development of AutoWebGLM, as mentioned in the paper?
The main motivation behind the development of AutoWebGLM, as mentioned in the paper, is to create a deployable web page browsing agent based on the ChatGLM 3-6B model that can autonomously accomplish complex real-world missions by navigating and operating on real web browsers like humans. AutoWebGLM aims to address the lack of a unified action space, the absence of a web page simplification method, and the scarcity of high-quality training trajectories for strong LLM-based web agents. By leveraging efficient data strategies and training methods like supervised and reinforcement learning, AutoWebGLM is designed to optimize web page comprehension, enhance interactive capacity, and improve web page navigation precision. The goal is to develop a practical and robust model that can handle the intricacies and variability inherent in web browsing tasks, ultimately revolutionizing how technology assists us in our daily tasks and interactions with the digital world.
How does AutoWebGLM differ from its predecessor, WebGLM, in terms of functionality and focus?
AutoWebGLM differs from its predecessor WebGLM in terms of functionality and focus by being dedicated to autonomously accomplishing complex real-world missions via navigating and operating on real web browsers like humans, whereas WebGLM focuses on retrieval-augmented web-scale question answering. AutoWebGLM is designed to enhance interactive capacity and web page navigation precision by amalgamating components into a singular framework, providing a comprehensive observation and action space for robust web browsing. In contrast, WebGLM does not emphasize web page navigation precision or interactive capacity to the same extent. AutoWebGLM leverages efficient data strategies to swiftly construct a reliable training dataset, while WebGLM lacks the capability for correct inference and self-checking on web tasks, struggling to rectify errors promptly. Additionally, AutoWebGLM introduces rejection sampling fine-tuning for lifelong learning in specific web environments, enabling the agent to become an expert in a particular domain, a feature not present in WebGLM.
Can you explain the concept of observation space in the context of AutoWebGLM and why it is important for web browsing tasks?
The concept of observation space in AutoWebGLM refers to the collection of critical indicators that provide essential information for the model to comprehend and operate effectively on web pages during web browsing tasks. The observation space includes components such as task description, simplified HTML, current location, and past operation records. Task description helps the model understand the objective of the task, while simplified HTML provides structural and content information about the web page. Current location information assists the model in understanding its position on the web page, and past operation records offer historical context for generating consistent subsequent operations. Incorporating these elements into the observation space is crucial, as it enables the model to handle the complexity and variability inherent in web browsing tasks by providing a comprehensive and standardized view of the web page environment. By utilizing a unified observation space, the model can maximize its capabilities by closely mimicking the information available on a browser's graphical interface, ultimately enhancing its comprehension and operational level for efficient web browsing tasks.
What are the key components of the observation space suggested for enhancing the model's web page comprehension and operation level?
The key components of the observation space suggested for enhancing the model's web page comprehension and operation level include task description, simplified HTML, current location, and past operation records. The task description provides information about the user's goal or objective for the current browsing session. The simplified HTML offers structural and content information about the web page, aiding the model in understanding the page's layout and content. The current location component helps the model determine its position within the web page, providing spatial context for navigation. Past operation records provide historical context, enabling the model to generate consistent subsequent operations by learning from previous actions and avoiding repetitive or ineffective loops. Incorporating these elements into the observation space aims to construct a resilient and practical model capable of handling the complexity and variability inherent in web browsing tasks effectively.
Describe the action space formulated for the language model-based web browsing agent in AutoWebGLM.
The action space formulated for the language model-based web browsing agent in AutoWebGLM includes various potential browsing operations such as click, scroll, and type. These actions are designed to enable the agent to interact with web pages effectively. The state transition in the decision-making process is determined by the current web page state and the agent's output action. The task ends when the agent outputs finish or reaches the maximum number of interactions. The function phi updates historical information based on the previous history, the most recent action, and the current state. The policy pi guides the agent in choosing actions based on the current state and history. The agent iterates through the policy and transition function until the action is finish, or the maximum length is reached. The action space is crucial for the agent to navigate and operate on web pages accurately, optimizing its performance in completing various web browsing tasks.
What are the challenges faced in constructing the training dataset for AutoWebGLM as mentioned in the paper?
The challenges faced in constructing the training dataset for AutoWebGLM, as mentioned in the paper, include 1. Task collection. Acquiring diverse, real-user task queries across various websites was a significant hurdle due to the need for varied tasks for training the model effectively. 2. Privacy and security. Privacy and security limitations hindered the direct acquisition of user browser operation sequences, making it challenging to gather data without compromising user privacy. 3. Objective annotation. The labor-intensive nature of collecting user objectives for each operational step made it impractical in real-world scenarios, as annotating each step for training data was time-consuming. 4. Model limitations. Current models could not process complex user queries across different websites, limiting the ability to use purely automated methods for accurate browsing trajectory collection in real and complex application contexts. To address these challenges, the paper proposed a hybrid human-AI data construction method to create the training data for AutoWebGLM, which involved categorizing data into 2 types: web recognition and simple task operation construction, and complex task operation construction.
Explain the 3 steps involved in the training process of AutoWebGLM as outlined in the paper.
The 3 steps involved in the training process of AutoWebGLM are supervised fine-tuning, SFT, reinforcement learning, and rejection sampling fine-tuning, RFT. 1. Supervised fine-tuning, SFT. In this step, the model is trained to comprehend the structure of web pages and perform basic operations based on user instructions. The model is equipped with the ability to execute predefined operations on the current web page, enabling it to understand and act on simple user commands effectively. This step helps the model learn the basics of web browsing tasks and prepares it for more complex operations. 2. Reinforcement learning. Following the SFT training, the model undergoes reinforcement learning to enhance its ability to operate the browser and infer tasks accurately. Self-sampling reinforcement learning is employed to address operational illusions that may occur during inference. By constructing contrastive data with positive and negative pairs based on the model's output and golden answers, the model learns from its mistakes and improves its capabilities through the DPO training approach. 3. Rejection sampling fine-tuning, RFT. In the RFT step, the model is optimized for specific web page environments in targeted domains. By sampling trajectories from an existing model and selecting accurate trajectories through reward signals, the model is trained to excel in particular web environments. Positive traces are identified based on successful task completion, allowing the model to become proficient in executing tasks within these specific domains. This step ensures that the model can adapt and excel in diverse web environments, enhancing its overall performance and expertise.
How does the model transition from supervised fine-tuning, SFT, to reinforcement learning in the training process of AutoWebGLM?
The model transitions from supervised fine-tuning, SFT, to reinforcement learning in the training process of AutoWebGLM by first utilizing the data constructed in the initial stages to equip the model with the ability to comprehend web page structures and execute basic operations. This phase focuses on enabling the language model to read and operate on web pages effectively. Following this, the model progresses to learning to plan and reason on the web by decomposing tasks into subtasks and executing subsequent steps based on the current web page and prior operations. This step enhances the model's capability to perform more complex web browsing tasks independently. After completing these stages, the model, now denoted as M_text SFT, advances to the reinforcement learning phase. In this phase, the model, having demonstrated some ability to operate the browser and infer tasks, undergoes self-sampling reinforcement learning to mitigate operational illusions. The model samples its output multiple times on complex task operation samples, constructs contrastive data with positive and negative pairs, and uses a DPO training approach to learn from its mistakes and further enhance its capabilities. By combining SFT loss with DPO loss, the model, now denoted as M_text DPO, stabilizes the reinforcement learning process and increases the number of training steps while maintaining its natural language and agent abilities, resulting in a more robust and proficient model ready for further training and optimization.
What is the purpose of rejection sampling fine-tuning, RFT, in the training of AutoWebGLM, and how does it optimize for specific web page environments?
The purpose of rejection sampling fine-tuning, RFT, in the training of AutoWebGLM is to optimize for specific web page environments by enabling targeted training through substantial sampling from an existing model, selecting accurate trajectories in instances lacking ones via reward signals. RFT allows the model to learn from its mistakes and enhance its capabilities by focusing on specific domains. By utilizing reward signals provided by the environment or pre-designed reward models, RFT helps the model to adapt and excel in particular web page environments. This training method ensures that the model becomes proficient in completing tasks within specific domains by learning from successful trajectories and refining its decision-making process based on the feedback received from the environment.
What are the main results and performance evaluations of AutoWebGLM on different benchmarks as presented in the paper?
The main results and performance evaluations of AutoWebGLM on different benchmarks as presented in the paper are as follows. 1. AutoWebGLM excels in predicting general user operation patterns, aligning well with user operations, showcasing superior performance compared to other baselines on the in-domain and out-of-domain splits, achieving a high step success rate SSR. 2. Mind2Web. AutoWebGLM's performance is evaluated using the MindAct framework, demonstrating its capabilities in web browsing tasks with a high level of accuracy. 3. MiniWeb++ and WebArena. AutoWebGLM is tested on MiniWeb++ and WebArena benchmarks, showcasing its proficiency in executing tasks across various websites and environments, with results indicating its effectiveness in completing web operations accurately. In summary, AutoWebGLM consistently outperforms other baselines across different benchmarks, demonstrating its robustness and practical applicability in real-world web browsing tasks.